Okay, so I wanted to make one small comment about the Ising model before we return to the business of the order parameters, which is one thing that I think I wanted to say but didn't quite say. Um, and that has some relevance to doing actual simulations. So just to remind you, so the Hamiltonian of the Ising model looks like this. So we have the actual interaction between the spins, and conventionally that's written with the minus sign, so that if you pick a positive coupling constant, that's the one that will favor ferromagnetism. So it's the one that wants to align the spins. And then I did write down a term, which is the coupling to an external magnetic field. And notice that the sum over the spins, that's effectively the total magnetization. So this term is the coupling of an external magnetic field to the total magnetization of your system. And so my remark is that it's important to keep that term when you do actual simulations. And that is apparent when you look at the phase diagram. So the phase diagram in this plane of H and T, okay, so that looks something like this. Okay, and here's TC. And we talked about this before. So this is a line of first order phase transitions that ends at the Curie temperature. And if I plot what happens as a function of the magnetic field below TC, so if I make a plot like this, so I plot H now on the x-axis and the magnetization on the y-axis at some fixed temperature but below TC. So, so if I plot this at some function, at some temperature T less than TC, then the magnetic field, the magnetization will tend to align with the external field, and then discontinuously jump. Okay. And remember that was different above TC, because above TC what's going to happen is that the external field will still tend to align it, but there's no more discontinuity. Okay. And so if you wish, the actual magnetization, the spontaneous magnetization of the system, you can view this as the H goes to zero limit of the magnetization at finite field. So in some ways, the thing that you're interested in, this magnetization, what we really want is the limit that H goes to zero, let's say with the positive sign, so coming from the right, of the magnetization at finite field. Okay. And then you see on this plot, you can see the difference between, so if you do it below TC, then this limit will be a non-zero number, so you get something like this. And if you do it above TC, so you come from here, but now the limit is zero. But it's important to study this, kind of limiting behavior, because if you make a study anywhere out here, in some sense, it's always impossible to know whether this is about to extrapolate to zero or whether this is about to extrapolate to a finite value, unless you actually study a couple of different magnetizations, study a couple of different external magnetic fields. So studying this kind of limiting behavior, that is making a study at finite H and then see what happens if you make H a little bit smaller, that's always an important ingredient of actually doing a simulation. Okay. And in particular, you can try to do a simulation at exactly 0 external field. But again, you have to be careful of the following phenomenon. Okay, so what can happen if you do a simulation directly at 0 field, or what will happen? So this is now, so we're doing a simulation at exactly 0 field. And what I'm trying to plot now is on the x-axis is just simply Monte Carlo time. So this is the number of Monte Carlo steps. Okay, and here's the magnetization in some given configuration. So this is magnetization. Then in a metropolis algorithm, so the magnetization will somehow fluctuate. So you'll see these fluctuations. So if you're at some temperature below TC, so let's imagine that we're at a temperature below TC, then the system wants to be magnetized. But if you do it in the absence of an external field, then of course the system doesn't know which way it's supposed to be magnetized. So in an Ising model, there's two possible directions. They could all go up or they could all go down. And in an actual simulation on a finite system, that actually will happen, that every so often the system will change its mind and flip, and then it flips back up, okay, and then it flips back down, and so on. So if you now perform an average over a very long Monte Carlo stretch, this will tend to average to 0, even though the system is magnetized. And so that's the thing that you prevent by running it at some finite external field, that's sometimes called tunneling, that if you have a finite system and the external field is precisely 0, then the system will occasionally jump back and forth. And so if you then take a long time average of the system, it looks not magnetized, even though it is. Okay? So that's one of the many things that one has to study if you actually perform one of these simulations. Okay? So that was a sort of digression. Okay, any more questions about the general metropolis business? So, so what I wanted to get back to is this question of order parameters and broken symmetries. So it's not obvious, by the way, that somehow broken symmetries have anything to do with phase transitions. Indeed, it was not obvious to people for a long time. There was, by the way, I noticed that the other day, so there was an obituary, I don't think he died of the coronavirus, but there was an obituary in the New York Times that Philip Anderson died 2 or 3 days ago. He was actually quite old, a Nobel Prize winner. He was in his 90s. I met him 20 years ago when he was already not that young. But he's the one person who actually, I think, I mean, the sort of realization that broken symmetries are important, I think it occurred to a number of people over the years, and then it sort of slowly drifted into the textbooks. And one person who was very instrumental was a Russian scientist named Lev Landau, and so it's discussed extensively in his textbooks. But in the West, a lot of people, myself included, really learned that from writings of Phil Anderson, that in looking at phase transitions, that somehow symmetries were crucial. And just to give you a rough argument of why that might be the case, so one way to think about the problem is the following. So I go back to that kind of phase diagram that I keep drawing. So now I plot magnetization, average magnetization as a function of temperature. And again, I assume that I've taken this kind of limit that I just mentioned, that what I mean by magnetization is kind of this limit that H goes to 0, but it's slightly positive, so that the magnetization will be positive as well. Okay. So then what we expect to see, again, is something like this. Just a magic phase transition. So that out here, the magnetization is really strictly zero. And roughly speaking, so the puzzle you're trying to answer is, how can it be, you could imagine, it's a complicated model described by a partition function that has a real interacting Hamiltonian. So there's various analytical methods, for example, that you can use. Okay, methods, for example, that are analogous to the use of perturbation theory in quantum mechanics, that you try to take into account that the spins are now interacting. And the puzzle you're trying to answer is, how can it be that anything is ever exactly zero? That, you compute some contribution to the average magnetization of the system that comes from the interaction of 17 spins or 18 spins or 19 spins, and you somehow do that order by order in perturbation theory. How can it be that the thing is just precisely zero? Why is it not just very small, for example? And in physics, typically in quantum mechanics or in statistical mechanics, if you want to guarantee that something is not just sort of zero, but precisely zero, you need some kind of symmetry reason why it vanishes. If there's no symmetry reason, then nothing is ever precisely zero. Okay? So roughly speaking, the idea is that the only way anything can ever be precisely zero is that this happens because it's protected by some kind of symmetry. And in this case, of course, we know what that symmetry is, because in the absence of an external magnetic field, again, there's no difference between all the spins pointing up and all the spins pointing down. And so any magnetization that is not zero would have to have some sign. And then the question would be, well, why is it positive? Because there's nothing in my Hamiltonian, if the external field is turned off, that would favor the value being positive over it being negative. So the symmetry in the Ising model is just a binary symmetry between up and down. Since there's nothing in the Hamiltonian that distinguishes up and down, it's not possible for the magnetization to be non-zero, because if it were non-zero, it would have to have a definite sign. Okay, so that was the sort of argument we started to go over last time in the case of a continuous spin, that if I imagine that I have some kind of lattice of spins, that the two possibilities, the spins could be kind of randomly oriented. So then any given spin, of course, does have a preferred orientation, but on average, there is no preferred orientation. So the mean magnetization, so this now has, if these are continuous spins, then the magnetization is also a continuous vector. So the mean magnetization is zero. And what that means is that if I perform any kind of rotation on the system, so I imagine that I rotate the mean magnetization by some kind of rotation matrix, okay, that of course is still zero, because any rotation of zero is still zero. So that means that in this case, the system is rotation invariant, because I take the mean magnetization, I rotate, and it's the same value. It's almost trivially the same value. It's because it vanished. Okay. So this is then a case where the system is rotationally invariant. And the other option, again, is now the spins have to point in some direction. Again, it doesn't have to be up. It could be any direction. The important thing, obviously, is that they're aligned. So now we have a situation where the mean magnetization is equal to some value, which is not zero. And now, of course, if I act with some kind of rotation matrix, then as soon as the mean magnetization is something, then a rotation matrix will now non-trivially act on this. Okay, so the rotated system looks different from the unrotated one, and so we say that in this situation, rotational invariance is now broken. Okay. So we always introduce this concept in the case of a magnet, because the symmetry in that case is kind of obvious. It's just rotations. In some ways, again, the even more basic example of a phase transition is what happens when you have a transition between, say, a solid and a liquid. It's maybe initially less obvious what the symmetry is in that case. So again, let me try to draw that example. So let's look at a, oops. Okay. So the idea is that the thing that happens here is that in a solid, obviously, there's a kind of preferred arrangement of the atoms. So, so there is some kind of lattice. And what happens in the low temperature phase is that the atoms now sit in these kind of preferred spots. Okay, and in the high temperature phase, the atoms are just randomly distributed. Okay, so the one thing that I can look at to identify a symmetry is the position of the atoms relative to the nearest vertex in my lattice. So, so the thing I can try to plot, and I'll blow up that plot later, is you can take a given atom and just look at this vector that connects it. You know, it sits in some kind of unit cell, if you wish, and you can always plot the vector relative to the origin of that unit cell. So the object you can look at is the position of an atom relative to the nearest lattice vector. Okay. And I can give that some name. Okay, let's call it Xi. So then what happens in the disordered phase, or in the liquid phase, is that this is on average is zero, because the atoms have no preferred placement relative to the vertices of this lattice. So in this phase, the mean Xi will just be zero. And as a result, this system is then invariant under both translations and rotations. So I can act on this with the translation, with the rotation, and I still get zero. And I can act on this with some kind of translation, and I also get zero. However, if you do this in the solid phase, so now they don't actually, again, you just superimpose a lattice with the right lattice spacing. You don't actually have to sit on the vertices of this lattice, just like in the magnetized case. It's not the case that all spins have to point up. It's just that Xi has now some preferred length. So this quantity Xi is now equal to some, sorry, let's call this the average Xi. So this quantity Xi is now equal to something that's not zero. Okay. And this, of course, means that now translations and rotations act non-trivially on it. What's maybe more interesting is to look at what a translation does. So if you act on this Xi naught with some kind of translation matrix, and so you say you translate by some vector A, then of course translation just simply means we take Xi naught plus A. Okay. So this is in general not equal to Xi naught. Okay. So it means that in general, rotational invariance is broken. Sorry, translational invariance. Rotational invariance is broken too. So it means that translational invariance is broken. But unless A is a lattice vector, if A happens to be one of the dimensions of the lattice, so it's a multiple of the spacing in either the x, the y, or the z direction, then it actually is a symmetry. So because then you're just translating the whole lattice by a multiple of its lattice constant. Okay, so one way to say this is that previously the system had a continuous translational invariance, so we could translate by any vector, and that was a symmetry. So previously it had translational invariance. Okay, and here this is only a discrete translational invariance. So the continuous one is broken. But a discrete version survives, and that's sometimes called a crystalline symmetry that survives here. And of course, the same happens with rotational invariance. So this system here, it had rotational invariance. In the solid system, the one with crystalline order, you don't have continuous rotational invariance, but of course, this is sort of a cubic lattice, what I drew here. If you rotate by 90 degrees, that's a symmetry. And so these lattices, they still have discrete rotational invariance. And indeed, all of these possibilities are kind of realized in various systems. So you can have a continuous symmetry that breaks completely. You can have a continuous symmetry that breaks to a smaller continuous symmetry, or you can have a continuous symmetry that breaks to a discrete symmetry. You can also, like in the Ising model, you never had a continuous symmetry. The only symmetry is discrete up and down. So you have a discrete symmetry that breaks to nothing, or you can have a discrete symmetry that breaks to a smaller discrete symmetry. So what effectively we've already done here is that we track the fate of these symmetries by choosing appropriate order parameters. So the order parameter that effectively I just picked in the solid liquid case was this average value of the position of an atom minus the location of the nearest vertex in a lattice. And so that's an example of an order parameter. So what is an order parameter? In full generality, it's a little hard to answer, but what an order parameter is some kind of coarse-grained observable that you construct out of the microscopic degrees of freedom. So the microscopic degrees of freedom is things like the orientations of the spins or the positions of atoms or the positions of molecules or the orientations of something that can spin. So there's some kind of microscopic variable, which is the thing that occurs in your Hamiltonian. So so you imagine that there's some microscopic degrees of freedom. And in the examples that we're interested in, the Hamiltonian will now frequently enjoy some kind of symmetry. if expressed in terms of these microscopic degrees of freedom, symmetries like rotation invariance or translation invariance. And from those microscopic degrees of freedoms, I somehow, by already correctly guessing what the kind of phenomenon is that we're interested in. So order parameters, again, there is no algorithm that allows you to identify an order parameter. You have to have some physical intuition or knowledge about the system to figure out what the correct order parameter might be. And that choice may not even be unique. That, for a given phase transition, there could be more than one object that will do the job. So we construct from this some kind of coarse-grained observable. By coarse-grained, what we typically mean is that you imagine that you take some large number of these microscopic degrees of freedom. So the whole system has 10 to the 23 atoms, and you can locally look at some neighborhood and say, construct an observable that somehow knows about the position of the nearest 1,000 atoms or something like this. So that's what's meant by coarse graining, that there's some scale which is much bigger than the distance between any two microscopic degrees of freedom, but much smaller than the overall size of the system. And so we have some coarse-grained observable, and we want that coarse-grained observable to carry information about the symmetry that we're interested in. So if, for example, the microscopic Hamiltonian is invariant under rotations, and we have some suspicion that what is happening in this phase transition is that rotation invariance breaks, and we want some observable that transforms non-trivially under rotation. So we want an observable that's a vector, for example. Okay. So in the sort of example that we discussed, so there were a bunch of spins, continuous spins. Something like this. And so what we have in mind is I take some neighborhood, like so, that's somehow big enough to have a large number of spins in it, but much smaller than the overall size of the system, so that in this ball, I can define some quantity, which is the mean magnetization centered around some coordinate x. Okay. So if I change that coordinate, I just make a similar ball that's centered around a different point. Okay. So that's a possible order parameter because it's coarse-grained, that contains information about many spins. And it's still local, so it can be defined everywhere in the system. And it carries information about rotational symmetry because this thing happens to be a vector. So it will in general transform non-trivially under rotation. Okay, so if Rx on this, it does something. Okay, so it changes the value. And so what is interesting about these order parameter fields is the following. Well, there are many interesting things, but one of the interesting things is the following. So let's now imagine we do this in this kind of symmetry broken phase. Okay, so then you have some system in real space. So this could be a two-dimensional system or could actually be a three-dimensional system. So a real magnet, of course, is typically a real three-dimensional system. So this is R cubed, and R cubed is just real space. So real space labeled by some vector x. Now, so this order parameter field is now some function from real space, it depends on x, it's a function from real space into the possible directions of the magnetization. And so if you're in the broken phase, then the absolute magnitude of the magnetization is somehow fixed by the underlying dynamics. Again, we get it from simulating this kind of theory. So we have a situation where in the broken phase now, the magnitude of M is fixed to be something, okay? But the direction is not fixed because unless I apply an external field, we don't know which way it's pointing. And so this means that the possible order parameters of this system, they don't actually live in a three-dimensional space, they live on the surface of some kind of sphere. Okay, so there's an order parameter space, which is the possible directions of this vector M. And so then what the order parameter field is M of X, what that is effectively is a map from real space, which is R cubed, into order parameter space. Okay. So for now, that seems like a somewhat abstract statement. Okay, we have this funny mapping that effectively goes from Euclidean three-dimensional space onto the surface of a sphere. And so why that will turn out to be interesting is because the interesting facts about the topology of mappings like this. So we'll see that the fact that the space on the left, real space, and the space on the right, order parameter space, are not the same. One is the surface of a sphere, one is ordinary space, means that there's funny defects, stable defects that can occur in magnets, okay? And so for now, we just kind of classify a couple of examples, and eventually we'll see that that plays an important role in governing what kind of defects and dislocations and stable objects you can have. So for now, I'm just collecting a bunch of examples of this sort of phenomenon. So another one that in principle we already discussed, okay, so that was the case of the lattice. So in the lattice, we had this situation that our order parameter was this displacement field, okay. So there's an atom here. Say an atom here. Okay. So that was this field Xi. So that was our displacement field. So we already noticed that the thing that was special about this displacement field is that it's not quite a vector, at least not an ordinary one, because two displacement fields are the same if they differ by a lattice translation. So if you have one displacement field Xi, and then you add to it some multiple of the lattice vectors, so say there's a lattice vector A in the x direction, I should really call that AX, and some lattice vector AY in the y direction. So then two displacement vectors that differ by a lattice vector are really the same. So what I mean by this is, again, this is just meant to be an integer. Okay, this too. The x and y's here are just unit vectors. And this is the lattice spacing. Okay. So what that means is that this displacement field, even though it looks like a vector field, is actually periodically identified. If I have two vectors that differ by a multiple of A, then it's the same vector. And so if, for example, again, this also applies to 3 dimensions, but let me, for simplicity, plot that in 2 dimensions, because that's a little bit easier. So if my real space is just ordinary R2, so that's where the atoms live. But my order parameter field, that does not live on R2, it lives on R2, which is periodically identified. So it lives on some space that really is only the size of a lattice cell, and it's periodically identified like this. Okay. And if you have a two-dimensional space which is periodically identified, that space is really a torus. Okay, so one way to draw this situation, okay, I'm going to have trouble drawing it. So this space is really a torus because it's on a torus that if you go around the x direction, you just come back. And if you go around the y direction, you also just come back. Okay, like so. So order parameter space, topologically, it's not R2, it's a torus or a two torus. So in the case of a solid, this map, which is psi of x, so the value of the order parameter field as a function of the coordinate is a map from two-dimensional space into a two torus. And if you did it in 3 dimensions, it would be a map from 3-dimensional space onto a 3 torus. And again, we'll see that that plays an important role for the kinds of excitations you can have in solids, that it's not just a map from R2 into R2, but it's a map from R2 into a torus. Okay. Just going to continue to provide examples. So another important example historically is superfluidity, which at some level we already encountered. So superfluidity is what happens to these Bose-condensed gases that you have below some temperature. You have a macroscopic number of atoms, all of which are in the same wave function. Okay, and so then effectively what serves as the order parameter here is the absolute magnitude of that wave function, because in this case, strictly speaking, that wave function may not be 0 precisely above TC. Yeah, actually, in some sense, it is. I was going to say, you know, in any event, you have at most sort of 1 or 2 atoms in it above TC, and then below TC, there's a macroscopic number. There's 10 to the 23 atoms in that wave function. Okay, but even that one atom, in some sense, averages out to 0 for reasons that you'll see in a second. So, so you have actually provide superfluidity. So the situation I have in mind, there's some 3-dimensional box filled with atoms. Okay. And my order parameter is the fact that I can now look at the wave function psi. Yeah. Let me just call it psi. So it's the wave function of these atoms in the ground state of the system. And so the dynamics of the system, again, will only specify the absolute magnitude of that wave function, because if you look at the Schrödinger equation, in the Schrödinger equation, you can always, if you find any solution to the wave function, you can always take that solution and just multiply it by a constant phase, e to the I phi, and that changes nothing about the system. And so, so the symmetry that you have here is a symmetry that takes that psi and just multiplies it by a constant phase. Okay. So if the psi on the left is a solution of the Schrödinger equation, then the psi on the right is also a solution, provided that phi is just a constant, doesn't depend on x. Okay. So that means that once the mean value of psi, so once psi squared is not equal to 0 because you have atoms condensed into the ground state, then the atoms can still pick a value of that phase phi. Okay, So that means that the analog of rotational invariance is some kind of phase invariance, and the order parameter really lives on some kind of circle. Okay. So when the system condenses, it has to locally pick a space in this, on this circle. So psi is some psi naught, but the system still has to pick the phase. Okay. And then finally, a cousin of that phenomenon happens in superconductivity. So in superconductivity, there's a similar field, but superconductivity generically happens in systems of fermions. So you cannot have an arbitrarily large number of fermions in the same state, but you can have pairs of fermions that are in the same state. And so in that case, there is a similar order parameter, but it's now the product of two wave functions. Okay. So for now, that's a little bit abstract, and we'll see how that becomes useful in just a little bit. Okay, but the concept is kind of important. So the important concept is that in a system with broken symmetry, you have these kind of two spaces that are floating around. One is the real space on which the system is somehow defined. It can be ordinary R cubed or some more abstract space like the space of all possible spins. And then there's some kind of order parameter space which somehow reflects the residual symmetries of this order parameter. Okay. So, okay. So really where this distinction comes in is when we look at defects in stable objects. But before we do that, we will look at something also related to the structure of the order parameter, which is the nature of elementary excitations in the broken phase. And again, that's most easily done with an example. So I think here I'm just following the book. And for simplicity, consider a two-dimensional solid. Okay. So we have a two-dimensional solid. So the system is characterized by this order parameter that we just identified, which is psi of x, where both psi and x are down two-dimensional vectors. But again, psi really secretly lives on a torus. Okay. So, so if you're in the absolute ground state of this system, then psi just has a preferred value. No, so the ground state is just psi is something. Okay. However, any system at finite temperatures, of course, never precisely in its ground state. So that means locally, the atoms, they're trying to be close to this correct value of psi naught, but in practice, there's always some deformations. Now, in a solid, that's effectively some kind of elastic deformation. If you took the solid and locally, it's crumpled up a little bit or it slants a little bit. And so locally, this psi is now not exactly equal to psi naught. And you can ask yourself, what is the energy that's somehow related to the fact that the position of the atoms is not quite right? Okay. So the energy, I mean, you can try to compute that from some kind of microscopic Hamiltonian, but you can write a sort of educated guess of what it has to look like, even without knowing precisely what the microscopic Hamiltonian actually is. And the one thing we do know is that so long as whatever the value of psi is, so long as it's just a constant, that's actually still a ground state. So, so any value of psi naught is in principle perfectly good as a ground state. What is not a ground state is if the value of psi varies from place to place. And what that means is that the energy of that state cannot really depend on the absolute magnitude of psi, because any of these is a perfectly good ground state. It can only depend on gradients of Xi, because it's not in the ground state if the position of the atoms relative to the lattice varies from place to place. And so what that means is that whatever the energy actually looks like, it must depend on gradients of this field Xi. And since the microscopic Hamiltonian was perfectly rotationally invariant, this energy should actually also be perfectly rotationally invariant. So this Xi and Xij, these are just vectors, but really it can only depend on absolute magnitudes, because otherwise there would be a preferred direction in the system, but there shouldn't be, okay? Now, in principle, it could be a function of this quantity. So it could be a function of the square of the gradient of the order parameter field, and that could contain arbitrarily nonlinear terms. But of course, if you're somehow close to the ground state, then we imagine that whatever variation of the position of the atoms you have is kind of slow. And so then you could imagine taking that complicated energy functional and expanding it out and just leave the first term, okay? So the first term is just some kind of constant times the gradient of Xi. And so conventionally that's called kappa divided by 2. And as I say, in principle, there could be many, many terms with more and more gradients, but if you're close to the ground state, these should in general be smaller. So these could be terms with more gradients. Okay. So I don't know if I can draw this. Well, I can try it on the next page. So effectively, what I'm doing here is something like this. So I imagine I have this underlying lattice. Okay, and I somehow encountered a state of these atoms where, say, on the left corner, the atoms were actually kind of located close to some given equilibrium position. But then as I go across, they initially shifted to the right a little bit. Okay, but then they changed their mind. And they're actually located a little bit to the left. Okay, so you could imagine drawing this as some kind of wave in the order parameter fields. Okay, so along this lattice, I could locally plot the x component of this order parameter field as a function of this x direction. So if this is x, and this is y. And then effectively the thing that I just drew is something like this, where here the value is 0, then I get to some kind of maximum amplitude here, then it returns to 0, and then it changes sign. Okay, so what I drew here is really some kind of elastic wave. And this expression that I just wrote down is really just the energy density of that wave. So there's 1/2 kappa gradient Xi squared is the energy density of that wave. Okay. Now, if I make a deformation like this in the system, then this is not the ground state of the system. So if it was not, in a thermal system, something like this could happen by thermal fluctuations. But if it actually was in the ground state and I made an elastic wave like this, then of course it would try to relax as a function of time. So, so in a real system, this energy that I just wrote down is really just a kind of potential energy, and assuming that all the atoms are in a fixed position. So what I could try to do is write a sort of Lagrange function that corresponds to this kind of potential energy. And what that would look like is something like this. Okay, so I would imagine that there's some kind of Lagrange function, which is T minus V, where this V is really the elastic energy density. Okay, and this here is some kind of kinetic energy. Okay, so so what is the kinetic energy? Well, we think that that's really just ordinary kinetic energy. So it's something like a half mx dot squared for these atoms. But up to a lattice vector, of course, x is just the same as psi. So we would imagine that this is some kind of a half m psi squared over the atoms. But psi is not an individual atom, but some kind of macroscopic field. So I shouldn't multiply it by the mass. I should really multiply it by the density of the system. So so again, effectively, this is just a guess, which one can try to derive from more macroscopic Hamiltonians. But the idea is that it should really look something like this. So this would be the kinetic energy. And again, the potential energy, oops, this should have a minus. The potential energy would be something like this elastic energy that I just wrote. And again, strictly speaking, there will be higher order terms. This will, by the way, then correspond to kind of nonlinear elastic behavior. Again, any system, if the exertion becomes too large, it becomes nonlinear. Okay. So, so what is amusing, as soon as I write down something like this, is I can try to derive some kind of equation of motion from this. So if I, if you think all the way back sort of 6 months to classical mechanics, this is the sort of system for which we can now derive an equation. And this one, of course, is particularly simple because everything is just quadratic. So this will indeed just be Newton's equation of motion. Sorry, it's somehow hard for me to avoid. I'm writing on my iPad, and it's hard for me to avoid that the phone will simply forward to the iPad. Maybe there's a way for me to turn this off. Okay, so what is the equation of motion? Well, it's just a regular Newtonian kind of equation of motion, which is rho psi double dot. And the other term we can integrate by parts so that we get kappa gradient squared of psi I. So that's the equation of motion. Okay. And then you can immediately see that this will have solutions that are kind of wave-like. So you can make an ansatz, which is that psi I of x and t is of the form that there's some psi naught e to the minus I omega t minus kx. And then you see that this will be a solution. So if you take 2 time derivatives on one side, so this will just bring down a factor of minus omega squared. So you get minus omega squared rho psi naught is equal to, and if you take 2 spatial derivatives, again, that brings down a factor of minus. So it's minus k squared kappa psi I naught. And then you can solve this for omega. So this says that omega is square root of kappa divided by rho times the absolute magnitude of k. Okay, so this is a standard wave-like behavior. So in the present case, we would call that an elastic wave. Okay. And what is important, I mean, that's sort of general wave-like behavior. What is important about this elastic wave is that so it has some kind of frequency. The frequency omega depends on the wave number k, and it depends on it in a kind of trivial way where if you take the wave number to 0, the frequency goes to 0 as well. So we have that omega goes to 0 as k goes to 0. Okay. So if stated like this sounds kind of trivial, but this is actually a profound observation. So it has a name. This kind of mode is called the Goldstone mode. So a Goldstone mode is just any mode where the frequency, or quantum mechanically, then the energy goes to 0 as the wave number goes to 0. So this is sometimes called gapless. Okay. And why is that important? Well, so if you take a system again that it's in its broken phase. In the broken phase, the ground state of the system, some of the order parameter points the same in all directions, but the system is not at 0 temperature. So there is some thermal reservoir and fluctuations always occur. But of course, the fluctuations are subject to some kind of Boltzmann distribution. And so fluctuations are governed by some kind of Boltzmann factor, e to the minus energy divided by kT. So the most likely fluctuation is some fluctuation that has a low energy. And what this says is that in a system with broken symmetry, there's always a candidate excitation that has arbitrarily low energy or arbitrarily low frequency, and that's a long wavelength fluctuation of the order parameter. And so the importance of this Goldstone mode for our present discussion is that this is with the mode that will somehow dominate the thermodynamics at sufficiently low temperature. Okay. So for example, what this says, as applied to a solid now, so in the case of a solid, so we have some kind of phase transition. We started, say, at high temperature with the liquid, but the system now solidifies. It's now characterized by an order parameter field. So in the present case, the order parameter field was this displacement vector. And now we want to know, sort of in general, without knowing anything in particular about the specific solid that we're looking at, is what is the thermodynamics of the system at very low temperature. And according to this, there's at least one mode that has kind of arbitrarily low frequency or arbitrarily low energy. So that can occur at any temperature, no matter how small. So any mode that has a finite energy will eventually become exponentially suppressed because of Boltzmann factors. So there's that one mode that will survive all the way down to 0 temperature, and that's an elastic wave in the solid. And what that means, for example, in the case of solids, is that if you want to compute, say, what is the specific heat of a solid as the temperature goes to 0, you don't actually have to know anything in particular about the solid. All you have to know is that it has this kind of broken symmetry and an order parameter field. And as a result, you already know that the specific heat will be dominated by elastic waves. And these elastic waves, they're really only characterized by one number, which was this kappa in our effective Hamiltonian. So, so what this predicts is that the specific heats of all solids at sufficiently low temperature must be the same up to kind of an overall factor, because this elastic energy, of course, is specific to the specific solid, but the general behavior is the same for all solids, so that at low temperature, all you see is elastic waves. And there's a fancy name for these elastic waves. They're sometimes called phonons. So at sufficiently low temperature, the specific heat of any solid is just dominated by phonons. Okay, so this existence of Goldstone modes is sometimes formulated as a kind of theorem. Which is indeed attributed, well, not just attributed, so that comes from Goldstone. So Goldstone was a person. So, so what the theorem states that if you have a spontaneously broken continuous symmetry, and strictly speaking, in more than 2 spatial dimensions. Oops. I'll say something about that in a second. So it leads to the emergence of a Goldstone mode. And again, a Goldstone mode is simply some kind of excitation where the frequency is proportional to the wave number if the wave number is sufficiently small. Okay. So, so why is it important to have a theorem like this? So there is a sort of similar phenomenon here to the one that I mentioned earlier. I mean, like you could ask, why couldn't there be all sorts of reasons why, that you have some kind of mode that as the wavelength of the mode goes to infinity, its energy goes to 0. And the comment is the same I made earlier. In physics, like if you treat this quantum mechanically, you can treat the frequency or the energy of that mode in quantum mechanical perturbation theory. And then in general, as you take the wave number to 0, unless there is a reason that the frequency is exactly 0, it will in general not be 0. So these kind of gapless modes, they only emerge for a reason. If there's no reason related to a symmetry, then no mode is ever precisely gapless, because there will always be some sufficiently obscure quantum mechanical contribution that will make it non-zero. So there has to be some kind of symmetry reason, and that's roughly speaking what this theorem provides. So if there's a spontaneously broken symmetry, then the theorem guarantees that this mode will indeed be exactly gapless if the wavelength goes to infinity. It requires the symmetry to be continuous. So it does not apply, for example, to this Ising model, because in the Ising case, the symmetry was discrete. So the possible states were exactly up and exactly down. And loosely speaking, in that case, so we really need a continuous symmetry. So, for example, it does not apply to Ising. And the part that's different about Ising is when I wrote down this functional for the elastic energy, I said that, well, I mean, if you have a sufficiently long wavelength mode, and this order primitive, you will, of course, kind of vary slowly from place to place. But in the Ising case, if you wish, that's never really true, because there's only 2 possible orientations. They're either all up, the next door neighbor is either the same orientation or it's exactly opposite. So this means in some ways you can never rely on the fact that you can write this down as just a gradient of some kind of order parameter field, okay? So, so you really do need the continuous symmetry. And the other restriction, the one with greater than 2 spatial dimensions, that's a more complicated thing. So it actually implies the calculation that I did just a second ago, which was really kind of two-dimensional, was actually, strictly speaking, not right, because what the example I gave was a two-dimensional solid. So so the 2D solid I just discussed does not actually have a Goldstone boson. And the precise reasons for that are kind of complicated. Actually, maybe not so. Okay. So in some ways, this really is somewhat technical, because all real systems, you know, nowadays you actually can make truly two-dimensional systems. So you can make a film that's just literally one atom thick. So that's a truly two-dimensional system in which this loophole to Goldstone's theorem actually really does apply. But the vast majority of systems in nature, even if they're very thin, they're rarely truly two-dimensional. So this kind of technical complication to Goldstone, the vast majority of systems, it really doesn't apply to. But nowadays, one can find systems, and one can indeed find that, you know, if you make a truly two-dimensional solid, then indeed it does not have a Goldstone mode. And roughly speaking, the reason is related to the fact that, strictly speaking, it never fully orders either. So in forming an ordered state, like a ferromagnet or a solid, it's always a sort of competition between energy and entropy. So somehow, you know, in the Ising case, we wrote down a Hamiltonian that favors the spins to be parallel. And so energy favors them to be parallel. But if you're at high temperature, entropy favors them to be anti-parallel. It wants to be as disordered as possible. And so roughly speaking, you can convince yourself that in two-dimensional systems, entropy will actually always ultimately win. That if the system is sufficiently big, then energy can never win over entropy. And in two dimensions, nothing ever truly orders. As a result, strictly speaking, a two-dimensional solid does not actually exist. A two-dimensional solid, if you make it sufficiently big, will always start to melt. And roughly speaking, Goldstone's theorem actually knows about that. So roughly speaking, what happens to Goldstone's theorem is you can assume incorrectly that a two-dimensional solid actually does exist. If it did exist, it would indeed have a Goldstone boson. And what happens to these Goldstone bosons because of entropy is, roughly speaking, that the Goldstone bosons become so strongly interacting that they destroy the solid. And so Goldstone's theorem, if one looks at it carefully, one really tries to prove it, actually discovers that. That's why there's this loophole that, strictly speaking, in exactly two dimensions and in one dimension as well, you cannot have a truly ordered state. And as a result, you can also not really have an ordinary Goldstone mode. Okay. And so I wanted to end today with a table that actually is kind of in honor of Phil Anderson. So this is a table from Phil Anderson's book. But I think, I don't know, I have to look. It may indeed be reproduced in our textbook as well, or at least discussed. So the book you may, by the way, be able to find it on the internet. It's called Basic Notions of Condensed Matter. Okay. Phil Anderson, by the way, so he did win a Nobel Prize. He won a Nobel Prize for the discovery of something that's called Anderson localization, for the explanation of something that's called Anderson localization, which is a kind of metal insulator transition. So the simplest kind of metal insulator transition is described by something called band theory, that you have this kind of notion that in the metal, the electrons can live in certain bands. And if your Fermi level, so the last field state, is in the middle of a band, then you can move an electron a little bit above the Fermi level and it can start to move and form a current. But if your Fermi level is between bands, then you cannot do that. And as a result, you get an insulator. And many metals are like that. If they have metal insulator transitions, that's because that's why it happens. And so Phil Anderson discovered that there were some materials which have metal insulator transitions, but they're not of that type. Again, there's some funny quantum mechanical phenomenon that causes the system to become an insulator. He was also kind of important, so that's what he won his prize for. But he did many other things as well. Again, there are actually arguably a number of things where he could have won a second Nobel Prize. He was instrumental, by the way, in principle, in pointing out to particle physicists what the Higgs phenomenon is. And so he could have arguably been included on the Nobel Prize for the Higgs phenomenon. And indeed, it's sometimes called the Higgs-Anderson boson. Okay, so he presents the following table, which is a sort of list of examples. So there's a variety of systems, and these systems have broken symmetries and order parameters. Okay, the order parameter is related to a certain symmetry, and the symmetry comes with a certain kind of Goldstone boson. Okay, and actually, strictly speaking, let me make a little bit of space here. Okay, there's a certain kind of rigidity phenomenon, which I'll explain in a second what people mean by that. Okay, so the system we already kind of discussed is a solid. Okay, what is the order parameter? One thing that, again, I already discussed is you can take this displacement vector, xi. Another thing you can do is you can take the density of atoms in your system, and if you form a lattice, the way you discover that experimentally, of course, is that you can do crystalline diffraction. And what X-ray diffraction measures is just the Fourier transform of the density distribution. So the peaks that you see by backscattering X-rays, you can also use that as an order parameter if you want. So another way to think about this is that you can just use the order parameter the density in K-space as an order parameter. Oops. That's an alternative way of thinking about it. Okay. Again, the symmetry in that case was translations and rotations. Let me just write down translations. Okay. What is the Goldstone mode? The Goldstone mode is this elastic wave, sometimes called a phonon, or sometimes also just called ordinary sound. So this is sound or phonon, okay, or elastic wave. And of course, the magic thing that happens to a solid as you cool it down from being in a liquid state is that it becomes rigid. So a solid is indeed rigid. Okay. The other example that we already discussed is that of a magnet. Oh no, I lost my board. Oh no, it's still there. Okay. So the other example is the example of a magnet. Again, in that case, the order parameter is the magnetization. The symmetry was rotation invariance. You have a Goldstone mode, and this is now some kind of magnetic wave that you have a preferred direction to the spin. So the average local spin direction is the local magnetization. And you can imagine tipping the magnetization a little bit, and then it will start to swing back and forth. And so that kind of magnetic wave is usually called a magnon. And that too is a Goldstone boson. You have a sufficiently large wavelength magnetic wave, so that has arbitrarily low frequency. And in this case, the system is of course also kind of rigid because it's permanently magnetized. So so it has phenomena like hysteresis. Another example that I already briefly mentioned is that of a superfluid. As I mentioned, the order parameter is now some kind of wave function. The symmetry is the phase invariance of that wave function. Okay, and now the Goldstone boson is a small oscillation of the wave function. So you're running around that little circle very slowly. And now you can just look at the Schrödinger equation to see what that does. So having a constant phase was just the symmetry of the wave function. But if you have a spatially varying phase, you do indeed have a small energy. And indeed, you get a density fluctuation and a current fluctuation. So the corresponding mode is actually in the end also just a sound mode. It's a periodic density, or it's a periodic density fluctuation. So this mode is also just sound. And the system is indeed kind of rigid, and here the rigidity is called superflow, so that the fluid wants to flow as a whole. And the final example that I wanted to give, again, the book lists a whole bunch, is superconductivity. Okay, in that case, as I briefly mentioned, the order parameter is really a kind of two-fermion wave function. And we'd have to do a full course in kind of quantum statistical mechanics to write it down more carefully. But the symmetry is exactly the same. So again, there's a phase symmetry. And this is the important, again, historically important example that Anderson discussed, is that this case actually does not have a Goldstone boson, because this is subject to another loophole in Goldstone's theorem, which I actually did not carefully discuss, which is that the would-be order parameter field is not electromagnetically gauge invariant. So there's no order parameter here. And this mode is sometimes called a Higgs mode, not a Goldstone mode. And again, but there is a sort of superflow-like phenomenon, which is called superconductivity. Okay. So again, in honor of Anderson, his famous table, maybe I just send you a copy, or I post a copy of that table on the Moodle site. Okay, but I maybe want to end here unless there's somehow questions. Again, just a reminder, so you have a week to take a look at the quiz. On Friday, so there's a Zoom link on the Moodle site. On Friday, I wanted to do a brief office hour in case there's interest, so we can talk about the homework, we can talk about the last midterm, maybe a little too early to talk about the current quiz. We could do that the week after. So, so either you can ask a question right now, or you can just wait till Friday and ask your question on Friday.